All right.
Today he taught us a bit about like doing circuit analysis on AC.
Okay.
Because I guess we're practically done with like the class. So he's like trying to give us a head start on like doing circuit analysis, like with AC current,
Okay.
and how you go from like AC to converting it to DC and then like back and
That's good.
using a couple different equations that we already kind of know, which is kind of
Basics in AC analysis, or just going into AC.
with like using E to the J theta with like magnitude and complex numbers. That one, yeah.
Tude and some complex numbers.
Yeah. So he was kind of teaching us how to go from like complex number going back and forth.
Okay.
So.
And then you can just have some EA real plus J imaginary, right? Something like that.
Yeah.
Well, that's basically it. But just as I was going to say, how we doing, everybody? Everyone doing good? How's the week? How's the semester? How's everything going? Not good? Why? Too much rain? Yeah, it's raining again? It's bad. Yeah. Our building's flooding. Our cars are slipping. This one right here.
This one's flooding?
Yeah, they're gonna make it so that the water bucket hits me right here, and then like pass out, and then like hardwire to say everyone gets an A.
Oh.
Hey, I'm
In that case,
I'm like,
I'm
no,
all for it.
nah, it's okay. But yeah. So
This building is honestly like leaking.
just one room, and then other rooms. One of the labs is flooding. You've seen the lab flood, right? Yeah, it was bad. It's okay. We've got our expensive $20,000 equipment out of there, so.
That's crazy. This building's only like what, like.
Yeah, it's our younger building too.
This is like one of the newer buildings.
I'll be mad if the AEB Advanced Engineering Building, if there's leaks in there, then I'd be like, what are you guys doing with my money? Give me that money. I'd rather buy equipment for you guys. You know what I get? Everyone in this class would get a kit. Be like, all right, the V in, V out, connect them or whatever, resistors, stuff like that. Maybe I'll bring an experiment next week. I'll think about it. But I wish I could have done a lot more in terms of maybe more physical hand-on things. But more point of this class is to discuss what's going on. How are you guys feeling LT Spice-wise? Maybe I could have shown you guys a MATLAB. MATLAB was mostly used for, what do you call it, MATLAB?
Yeah, because I've seen that, and I was like, I've never played with that.
It's one of the best tools in the universe, from my opinion, because I'm a MATLAB enthusiast. It's where you can do a lot of signal processing. Okay, I'll preview you guys. If you guys want to know what MATLAB does, you can do some.
You kind of playing with it right now.
You can literally do mathematics. Like here's our delta time, right? DT. I'm stepping in 1 milliseconds, right? Here's my time, correct? Here's my unit step, correct? I'm creating a unit step function. You guys know what a unit step is, right? Right, unit step? No?
I've never heard of it.
Okay. Because you guys are going to be studying this a lot. Technically, you should be knowing this. You should know. You guys know this. What?
Have you guys?
For my Pushkin students, come on. I think it was because I've seen your guys' notes. Let's see. Prove me wrong. Did he talk about it? Let's see. Modules. Chapter 5. Yeah, the ramp signal. You see, is there a unit step? Yeah, you see that right there? Well, there it is, step function. So unit step, that's another. You see that U of t right there? That's it. That's a unit step. So in other ways, it turns on at t is equal to 0, correct? Ramp function, right? Turns on at t, whatever that is. Okay, feeling good. Exponentials, right? Okay, this is good for you guys. This is good. If you guys want to do this homework on MATLAB, unit step, right? So, okay, this is Boolean algebra, correct? T is greater than or equal to 0. Return true, right? You see this right here? This T, correct? We have negative numbers, right? Let me turn this to 1, right? 1 second, okay? 1 second increments, okay? So I'm going minus 10, minus 9, minus 8. No one believes me. Run. Let me show you this train. Come on. That's a bad way. Here's our time. 10, 9, 8, 7, 6, right? All the way to 0, correct? So we want to turn on right here, right? Our unit step, correct? So give me, okay, true, return true if greater than or equal to the 0, right? Right? And then return false if it's this, right? But what's another way of writing true and false? 0 and 1, right?
Yeah.
Boolean from CS, right? You guys took your CS class. How's the CS class, right? How's that going? Pain?
I'm taking it this semester.
Okay.
It's not as bad as I thought it was going to be.
Not as bad?
I thought it was, like, I signed up for it many semesters ago because like, what, 5 years ago when I came back now.
All right. Would you have rathered us?
2020. And it wasn't as hard as I thought.
Would you have rather us drop that class and then we could have given you guys an intro to MATLAB or intro to Python class? This is Python right here. Or MATLAB Python. It's a scripting language. So all you do is you see how straightforward this is.
Here, Python is like, it's like straightforward.
It's the engineering coding language.
You don't have to go through like the little additional steps.
Well, you can do some crazy stuff going around here and build your own functions, and it gets pretty heavy. See, this right here is a function right here. I'll show you guys later. Anyways, let me see. What was I trying to show you? Yeah, right here.
We're doing the Boolean, the true and false with the second.
See this right here? True, right? Return true, okay? And then this is my exponential, okay, right? It's exponential, right? Exponential e to the minus t, correct? And this right here is e to the minus 3t. And I'm putting a unit step, multiply that by the unit step, correct? Right? So that means I should expect this one, well, it's just going to be e to the minus t, correct? Okay, and I don't know if anyone's following. So if I were to do e to the minus t, correct, right? When t is equal to 0, right? What's e? Or what's this value?
1, right?
1, right?
Yeah.
And then it goes down like this, it decays, correct? What about when we go backwards? Goes up, right? That looks an exponential. Goes, woo, right? And then what about e to the minus 3t, right? What's that? When t is equal to 0, what's this function?
1.
Also 1, right? But it decays faster, right? So it decays much faster, like that, right? Correct? But let's say I multiply this by u of t, correct? If I multiply this together, what happens? So this is our unit step, right? This is our u of t, correct, right? And this right here, let's just finish this. This right here is this right here, right? If I put these two together and mesh them, like you see how this correlates with this section, right? And then what happens to this guy, this section right here? It just disappears because we're multiplying this by zeros and this whatever the value is, correct? So now we get e to the minus 3t u of t. So it just does this. And then it's always, when t is less than 0, right? This value is always 0. Does that make sense? You guys want to see it?
Sure.
Right? And then this right here is just convolution. Don't worry about it. That's for our advanced engineering classes. Boom, check. We just want to run this. F9 for evaluate section and command window.
So in this program, is that the percentage kind of like in CS where it's the // like comments?
Yeah, basically comments. Not that hard. Now let me show you what this plot looks like. Looks cool, right? All right, here's our 0, right? And then it just gets bigger, right? It's kind of too big. Yeah, that's why I did this. Let me show you. F9. Does that look like a unit my input? Did I mean excellent? Wait, hold up. Evaluate this. Yeah, evaluate that, whatever. I'm going to set the window to -2 and 5. The time, okay. Let me show you what this does. F9. See, now we're at -2, right? -2, -1, 0, 1, 2, right? That's our time, correct? And it just gets bigger here, right? That's that's X right here. I'm calling it this right here. Now I want to plot H. Let me show you this. There we go. F9. These are bad. You want to know why? It's because I need to set this to something more precise, more analog. 1 millisecond. Okay, now let's rerun all this. F9. That stays the same. Run this again. Oh, come on. There you go. F9. Boom. You like that? You see that unit step? The unit step's being multiplied to this. Don't believe me? Let me get rid of the unit step. Boom. It's gone now. Like that? No, we don't like that. It disappeared. What happened? I don't know. You tell me. Run. See? The unit step's gone now. Cool. What if I wanted to delay it? Let me delay it by 1 second. At t is equal to greater than or equal to 1 second, return true, right? 1 second delay. 1 sec delay, right? I'm going to run this. And then actually dot times u1. Let's run this puppy. F9. And let's just run the whole thing. There we go. You guys are going to see this if you're all electrical engineers. Let's see. What did it say? Unrecognized function. Oh, it didn't like that. Screw you. There we go. 9. Boom, 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 boom. Evaluate. Delayed. See that? Now we're delaying our things, okay? Is that making sense? See, unit steps. Okay, and then someone says, David, I hate this class. Just plot the unit step. Okay, we'll plot the unit step. You want the unit step? Fine. Plot unit step. U1. Let's plot this puppy. F9. Unit step, right? And you guys want the one that starts at 0? I called it U0. Unit step 0. That's what I've been calling it. F9. See? Delayed at -1 or delayed 1 second. Boom, right? At 0. Is that making sense? Any questions about that? No? Let's close this one. Oh, I guess it's saved. Oh, it did save. Whatever. But yeah, MATLAB can do a lot of things. It's not just meant for, plugging and chugging. You can do a lot of crazy stuff. But anyways, is that making sense? All right, so what else did we talk about in class? AC analysis.
Yeah, we talked a little bit towards the end about that.
Are we doing?
We're pretty much done with the chapter.
Okay.
We went ahead and covered. We went over a problem with the second order op amp circuit.
Okay.
We did that, and then we did.
Let's see what the homework says.
Did another problem.
Chapter 6, problem 12. Let's see. Problem 12. Is this just continuing more RC circuits? Or LC? Stuff like that. Determine VC in the circuit. Right? Do you know how to do that problem? Not that hard? Not too difficult? Want us to do it? Yeah, let's just do it. Plus, minus. Don't worry. I know the camera's not watching or whatever. Let me see. Let's see. Okay, I see what's going on. Okay. I'm going to draw this. Okay. People want to see what I'm doing, right? Yeah, because you're probably giving us a trick. I know I'm tricking you guys. You guys figured it out? Okay, doing that. Here's our resistor. Boom. Inductor. How do you guys draw your inductors? Oh, you guys you guys like a curvy?
Yeah, little swiggles.
Yeah, swiggles. I just do this and call call it a day. I don't know. Anyways, let's see. Got some L. We got some capacitance, some charge in this capacitance, some inductance flow, correct? Then R2, R1, and then what's over here? V naught, VO, V initial, and then T before 0, right? It's closed, okay? It's so the whole circuit's closed, all right? So what are our initial values in the circuit? Okay. Let's think. Okay. So the problem says at t is equal to 0, right? When t is 0, right? The circuit opens. Okay? So let's not think too deep, okay? Let's see. Oh, V naught is 12 volts. R1 is 0.4 ohms. R2 is 1.2 ohms. This right here is 0.1 Henry and 0.4 farads. There we go. Use a time scale that appropriately. Okay. You gotta draw this one. Okay. Draw the charge or the voltage drop in this. Okay. So let's draw. Let's have some fun. 0, right? And then before this right here is t is less than 0, right? Let me just write this over here. Okay? Right? And we're trying to calculate VC, right? We're trying to draw it. What does this look like on an oscilloscope, okay? So we know that the wire is it's closed, right? It's this is right here is just the wire, right? Okay? What's the voltage over here? I don't know.
Capacitor DC?
Yeah. Actually, better yet, what's this inductor at DC? Okay, we have current going through here, right? Or something, right? Over long periods of time, what does the inductor look like? Or what does it act like? It's the wire, right?
It's a short, right? The wire?
It's just a short. Like, if you think, like, let me see if I got this telephone cord, right? You see this wire right here? Yeah, that's kind of like an inductor. But in the end, it's just a wire, right? It's just a piece of wire, okay? At DC, we're just stable, okay? Nothing, we're doing nothing, okay? So that voltage right here, right? Or what do you call it? So the voltage difference, right, is going to be 0, right? It's just a short, correct? So if I call this one, I don't know, Vx, correct? What's the voltage over here? Vx, right? But what's Vx? Vc, right? So technically, this right here would also be equal to Vc, right? Is that making sense? All right? What's the current in this circuit then? If I were to draw, well, actually, what's the current in this capacitor? What does a plate of two metal plates in this circuit, like what's the current going through that? Or what does it act like? It's an open, right? It's just two plates, right? It's just literally, how do I explain this? I don't have two plates on me, but think of it like literally just two plates sandwiched like this. There's nothing to connect it. I like using analogies, okay? So, anyways, no DC current is going to go through that. 0 current, right? So that means there's no voltage drop, and then there's there's going to be this voltage drop right here, right? Because the capacitor is going to store a charge, correct? But there's no current here, right? That's good. All right, we're happy, right? So what does this circuit turn into? What does it look like? I don't know, man. You draw it for me. I'm too lazy. I'm just here to think about my next meal. It's okay. Me too. I'm hungry. 0.4, 1.2. What does this look like? Voltage divider. Voltage divider. Good. How do we do that? 12 times the resistor we want, correct? Divided by the sum. Yep, sum of R1 and R2. That's 1.6 on the bottom. Does someone want to do this math for me?
It's 1.2 over 1.6 times 12, which is going to equal 9 volts.
9 volts?
Yeah. So you have 1.2 divided by 1.6 times the initial voltage, and then that gives you 9 volts.
9 volts, right? Is that what everyone got? Is that good? 9 volts. Good? So what is before time our things close, right? Our switches close, right? What's our voltage? 9 volts. 9 volts. Great. Good?
Yes, 9 volts. Yes.
All right, now this is where the fun part starts. Page 2. Do I want to do it on here? We'll think about it. Actually, okay. So now our switch opens, right? T is opening, right? Boom, right? At T is greater than or equal to the 0, now our circuit's opened. Open, right? So now we got to redraw our circuit. Okay, I like redrawing things. It helps me. I'm a visual learner. That's the way I learn. It's easier for me to study. 1.2 ohms, 0.1 henries. Put the resistance here. Capacitor. I'm going to draw a ground symbol because it makes me happy. 0.4 farads. Boom, 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 boom. Is that looking good? Right? All right, so we have this capacitor, right? It's got some charge in it, right? What's the voltage in this? 9 volts. Right? 9 volts, right? Is that good? It's just a bank. It's just a storage charge, right? It's just storing some type of charge in there, right? However, now we have this inductor, right? And now it's going to start generating a current. All right? This doesn't like changing currents. It doesn't want to change. This one doesn't want to change current, and this one doesn't want to change voltage. All right? But now we're going to have this point where this is going to start discharging, and then this one's just going to steal all the current that's going through there. Okay? Does that make sense? Anyways, let's see. Well, I know we're going to have an RC constant with this guy right here, right? And then we have an inductor right here. So, how do I want to try and do this? Do I remember? Let's see if Dave remembers. I'm not remembering. You guys remember? How do I solve this problem? What's the first step? What's our magic equation? We don't know. We didn't come to class. Me neither. I didn't go to class either. Anybody?
Is it that equation of VT?
VT?
Which one is it? The one where it has E2 whatever? No, right?
Oh.
Yeah, where it's a derivative, no?
Well, with this guy right here, right? This RC constant, we're going to have a time constant with this R and C, correct? Right? And then, well, if we have some VT, correct, which is, I'm trying to remember, was it V final minus V initial, right? I'm not remembering this one. What's that equation that we were always memorizing? Was it V final minus V initial? Or V initial minus V final? I don't remember. How do I want to try and do this? Well, we do know we have VL plus minus is equal to L di dt. That's the current in there. This way we have the actual current, which is I is equal to C dV dt. How do we want to solve for this puppy? Because I know what's going to happen is that these two equations are going to want to bother each other because this current is dependent on this current right here and the voltage. You see, we have a change in current and a change in voltage. We have two sources that are trying to fight for each other. We have a second order equation. They don't like each other. Is that making sense? Anyway, let's see how I want to solve this. Plus, minus, how do I want to do this? Plus, minus, no, wait, no. Our current's going this way, so that means plus, minus, plus, minus. Let's just go over the fundamentals because I'd rather just go through that. Inductor, capacitor, boom. I'm going to call this one R, L, C, okay? Plus, minus, plus, minus, plus, minus. Let's do KVL. Okay, let's not forget this, okay? And this is IL, right? And this is VC right here. That making sense? Good. What's the first step? Draw our current, right? Second step, walk the circle, plus, minus. We're going down the stairs, minus RIL, right? Going down the stairs, what's the voltage here? VL, right? VL is equal to, what do you call it? LDIL dt, right? Is that good? DIL dt. Yes? Then down the stairs, minus BC equal to 0. Is that good with everybody? And then, because I don't like negatives, we're just going to multiply the whole thing by minus 1. Because we have a 0 on the other side, we can do that. Everyone like this equation? No, I don't like it. It's painful. Anyways, let's see. We have a derivative here. We have this. Well, if we know IL is equal to, what do you call it? CD, what do you call it? CdVC over dt. Okay, that's that. But if we want to get this guy right here, okay, I'm seeing what's going on. So if we do IL dt over C is equal to dVC, right? And then I try to do an integral. But this right here is a function of time, okay? If I integrate this, right? VC is equal to the integral, right? Of, well, 1 over C, right? ILT, right? DT, right? Is that good? Is that something good? What do you guys think? An integral? If I were to do the following, RIL, right? Plus L DIL, right? DT. Plus, if I were to punch this puppy in, C, right? And then I have this fat integral. Because I'm wondering how he solves it. I'm wondering if I'm doing it the right way. So we have a derivative, we have something constant, we have an integral, right? So I'm wondering, and I really don't want to push you guys in this direction, because I think this is a cheat for the next semester. How did he make you guys solve this? Did he take a derivative of this whole thing? Is that what he did?
I know he did derivatives, but no integrals, right? I don't recall either. Yeah.
So did he do the following? D over dt.
What's that?
To where you get the following. R, D, I, L, right? Did he do this? L, D, there we go, D2. Did he do this? Plus 1 over C, I, L. That's it. Did he do this? A second order equation?
That he did.
All right.
The second order equation does sound familiar.
This is page 3?
Yes.
Let's go on the next page to clean this up. So I can show you guys what I was trying to do. See what I was trying to do right here? I took a derivative of this whole entire thing, okay? Right? Is that making sense? I got rid of the integral. The derivative got a second order. And then, well, this constant turned into a derivative, right? Is that making sense? So let's reorganize this. I'm going to put the second order guy right here. L. And is anyone bothered if I do the following? I, L, that. Is anyone bothered by that? Plus R, I, L prime, right? Plus 1 over C, I, L is equal to 0. What did he do after this? Did he go into the Laplace transform? Did he do Euler's equations? Where he said maybe a general solution, right, to this IL, some general equation could be like some form of e to the, what was it? E to the t, or what was it called? E to the AT, right? Something like that. Was that something familiar? Right? So where you have to do the following if you were to do some, what do you call it? So let's get rid of this. We can divide this whole thing by... Divide this by L. He divided the whole thing by LC?
But not at that point. I'm trying to recall what he did before the decimal point.
Because it can be rewritten like this. IL plus RL, right? IL plus 1 over LC. Right? So now you have the time constant here, R over L, and this one here, which is L over C. Right? That making sense? And then the other thing you can probably do is, did he do anything with eigenvalues, eigenfunctions, auxiliary equations? Yes, no, maybe? He
I
didn't?
don't think so. Yeah, no, that doesn't sound like something I've heard.
So how did he solve this problem? Did he just give you the equation? What is he doing? Because what I was trying to say was you can turn this derivative into something more fun, which is like this. Let me see. If you were to replace it like this, lambda plus R over L, lambda plus 1 over LC is equal to 0, and solve for lambda. Did he do something like that?
He didn't even know that.
No lambdas.
No.
And he did solve the cost of the factor part for that equipment later, but that's later stuff.
So how did he solve this then? Let's look in his notes. Let's see.
What he covered a lot was like the
He referenced more so like the two numbers, I think 6-500, 6-10 today.
Let's see. How did he?
like he told us he emphasized a lot on table 6.2.
Table 6.2.
Table 6.2, yeah, he said make sure you know this for this equation.
And he used the table in column 2, by the way. One in this bunch.
Yeah, but in our book it was correct. That's the one I pointed out.
Where's table 6.2? Okay, this right here is table 1.
Yeah, he told us to know that.
And that's a Laplace. Is this a Laplace transform? This ain't no.
He told us
And then there's another table after this one.
he told us to ignore like the A1 equals A2 equals stuff. But just like I don't
Because he taught us like a more condensed way of doing it. Not like to not make it overcomplicated.
Table
That
6.2.
one right there, that's like the equations we use like pretty much the whole time.
yeah.
That's how
Your
he
unknown variable. Oh, you see, he did do it. Kind of. Sorta.
It just looks different, like with the integral and all that. Like we didn't use that integral.
Man, he really went pretty deep onto this.
Yeah, that's what like he emphasized a lot on that.
Alpha is equal to, and then he says you can. He's going straight for the Laplace transform. This is great.
Is that a good thing or bad thing?
It's a good thing because I'm showing you the right way of doing it, but he's telling you to memorize it, and you basically don't know why you're doing it.
Oh shoot.
So basically, am I doing my job? I shouldn't. Well, technically, they should be teaching you how to do it. I shouldn't. Well, solve for lambda, okay? So this is the general equation. Okay, this can also be voltages, okay? Yes? Yep, this is a differential equation. Second order differential, ODE. Yeah. Wait, so what was required for this class? 182? Interesting. Yeah, because technically you do need enough second order equations to get through this problem. Because you guys wouldn't even... Math 431?
No, like me and him, we're in Calc 3. We're in 283. He is too. And we're taking this class. So I think we're a little off.
That's why they're making you force this. They're like, we're too lazy to show you this. So anyways, I guess I'm giving you guys cheat sheet answers.
Yeah.
There. No, because now I got to teach you guys to... But yeah, basically the way I'm doing this is through mathematics, the way the engineers gotta like brute force this. Like it's not that bad. That's the reason why like I crashed over here. I was like, what the heck do I do? Well, I do know you can turn this into a second order equation. This becomes a lot easier. So if you wanted to do lambda squared is equal to, quick, sing the song. Lambda, get rid of that. is negative b plus or minus the square root of r squared L squared minus 4ac LC, right? All over 2.
That's actually interesting at all. You should know this. I haven't done it in years.
Which, honestly, this is ugly. I don't like this.
Yeah, no, I do like
This is painful. Nah. So there's definitely a better way to do this because I think, let's see, x0, and you know the initial condition. Okay. You know that. You know the settling time, where C and B. What is C? C is whatever this is. Okay. Oh. Okay. Alpha is this, because I want you guys using these equations if that's what he's talking about.
That's what he like talked about. That's what he emphasized with using that.
Well, you kind of skip like the bottom part of the overdamp one, the bottom two parts. In most books, it's the X and T one.
Mm-hmm.
Really look like that's doing too much. That's why this factor is not to find that I want to find the 2 points or the 2 constants at that point.
Yeah, because this one, you need to know the initial condition of the derivative. And this one, we only know this one right here. What do you call it? The initial condition itself. That's what we know. So this is technically gone, right? And this right here too. Why is he giving A1? Well, this can be punched into this equation. You're going to get 2 sinusoids out of this. This is ugly. I don't like this.
So that A1 and A2 are just constants.
A1 and A2 are constants. Yes, that's because this is going to give you a constant. But what is S1 and S2? This right here. You know what? Let's Okay, let's try this again, engineers. Page 4. Let's reverse dissect this. Because I want to make sure you guys are well aware of these equations you're going to be forced to memorize. We got to memorize equations? Yes, because we're here to make money. I don't want to make money. I just want to pass class. X plus AX plus BX is equal to C, right? Okay, that's some general equation, but let me write this ghost equation right here. Or not a ghost equation, it's just what we're going to eventually solve. Let's see. I'm going to write it in orange. IL, actually, no, I don't want IL. I want, we'll save you for later because we need to get stuff done. I need to write this equation in terms of voltage because that's what I want. So let's see. You guys messed up like me. We need, we take a derivative, correct? We need to get to a derivative to start doing auxiliary equations, right? You see this right here, this VL, right? But the derivative is I. No, I want V, okay? So the way we solve this is with KCL, okay? So we're going to redo this problem for KCL, okay? Okay, let's do this. Because I don't want to waste more time. I want to do more math. What do you call it? Proving. R, L, C, okay? So this right here, let's see. How do I want to do this? What's the current? What's the total current? Well, the total current, how do I want to say this? This here is VC, but how do I want to show you this in terms of current? Because the current in here, let's see. Well, we do have this, plus minus, right? Where, how do I want to show you this? Well, current in I, the current in here, IC, right, is equal to, I is equal to C dV over dt, right? That's the current in here, okay? This is guaranteed, okay? That's a guaranteed current. You know that, right? But right here, let's just see, is IR. I'm calling this IR, okay? if I were to do a KCL right here, right? What's the current going through here? Or what's going in? IR, right? Or how do I want to show you this? IR, right? Which is equal to IC, right? Is that making sense? Okay. Well, technically we have this IC and this IL, or I'm trying to figure this out. Because technically this voltage right here, how do I want to show you this without making it too complicated? Because what I'm trying to show you, because we can technically solve for the current in here, but then all we have to do is we've got to divide that current by the resistor. And I don't know if I want to do that. Do you guys want to try and do that? It might be easier. Just solve for this problem instead. Yeah, let me show you what I was trying to do, because I don't want to waste more time. Anyways, let's write our ghost equation. IL prime, right? Plus RL I prime, okay? Plus 1 over LC, okay? Gonna get rid of these L's. Okay? What is our alpha term? R over L, right? Right? And then what is our B term? 1 over LC. Is that good? Okay. So now, what is our settling? So basically our current, okay, let me show you this, because I don't like this problem. I want to make sure they know what you're doing. Our X, right? That's our current, right? Our X, right, is equal to our I. That's where we're trying to plug and chug. We're solving for I. So it's saying our settling current, X, or what do you call it? I, as t goes to infinity, right, is equal to C over D, or B, right? Where C right here, right, is 0, right? So if I punch in 0 here, right, our current's going to be 0. Does that make sense? Yes? No? Because we have an inductor. As time goes to infinity, the current's going to be to 0, right? There's no current in this. Does that make sense? Okay? So let's see our alpha term. Let's write this. Alpha term is equal to A over 2, which is equal to this R over L, right? If I were to punch that in. It's, R over 2L. Is that good? And our omega naught is B. I don't like this. Square root of this. Is everyone okay with that? I'm just setting this alpha term to this right here. And that omega naught term, that's our resonant frequency. Resonance. We're going to have a wiggly line. Let's see. It's saying compare these two values. Compare alpha and compare omega naught. So what is alpha? Our R was equal to what? Let's see. R was equal to, what was our value for R? What's our resistor? What is R? R was 1.2. I'm just going to write this over here. R was equal to 1.2 ohms, okay? Our L was equal to 0.1 henries. And our C was equal to 0.4 farads, okay? So we just got to plug and chug our numbers. So our alpha term, right, is going to be equal to 1.2, right, divided by 2 times 0.1. What's that equal to? Well, this is going to be that. Someone help me out. Calc.
What is it again? What are the numbers?
I got this. Let's see. So 1.2, right, divided by 2, that's 0.6, right?
Yep.
But then that number is going to be divided by 0.16. So alpha is equal to 6, okay? What's omega naught? Omega naught is equal to the square root of 1 over 0.1, and 0.4. So what's omega naught equal to?
So 0.1 times 0.4.
1 to
0.04, so 1 divided by 0.04 equals 25, 5.
and then yeah, square root.
Yep.
So that means this right here is true. 6 is greater than 5. Is that good?
Yeah.
So now,
That NP, sorry to interrupt. The NP, is it pronounced Nepper?
which one?
For like the units?
Units.
Because like I have the answer or whatever, but it says NP over S. Is that Neppers?
NP over S.
Yeah. Because someone else asked that question like in class for like the units.
You know what? Okay, let's just keep going. So we're gonna use this equation. Okay, that's why we were trying to do this. Okay, the current's gonna be wiggling. Okay, overdamped, or is it overdamped? Resonating? Yeah, it's okay.
Yeah, it's over.
Over?
I believe so.
Is it wiggling? So we got to solve for A1. What's A1? This is 0, right? Can everyone agree the initial current was 0? Right? And then our initial, or the derivative of the initial current was 0. The initial current itself, man, I don't like this, man. If I were to solve this, because we want to solve for this, we knew the initial current right here was 0, right? But then, what's this called? Let me see. If I were to go back here, right? Let me see. What's page 3? Page 3. Where's my page 3? We had the 12 volts or the 9 volts in here, right? 9 volts, right? But we just said that this right here, Vx right here, was equal to Vc, correct? So that means there's 9 volts here, right? What's the instantaneous current? 9 volts divided by R. I0, right, is equal to, well, our I is going the wrong way, okay? But I'm just going this way, okay? We got minus right here, right? Okay. IL, right? Plus minus, right? Is that making sense? But I want to know this initial current. So what's at 0? What's at V plus? 0, right? What's at the minus? Divided by R, right? Which is 1.2. What's minus 9 divided by 1.2? Ugh.
Divided by 1.2?
7.5?
And negative 7.5.
Negative 7.5 amps. That's a lot. That's our initial current. Pretty crazy, right? So that means you would plug that guy in here, and then our settling current is 0. And then what's S? Man, this is painful, y'all. Is this what he's making you do? I don't like this. Man, you guys are getting it rough here, huh? Let's get to the answer, because that's what I want. Switch. Okay. Here's my switch. You guys like my switch? Nintendo Switch. What's our circuit? Are you guys getting good instruction, or is it poor instruction? Poor instruction, man. I'm confused. I'm tired. Me too, man. Me too. Let's see. Because I would have done this a lot differently, because I don't want to use these equations. I'd rather just plug and chug. Let's do this. What do you call it? Is anyone bothered if I do the following? Let me see. Boom, 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 boom. Okay. Voltage source is, I'm going to call this my switch. V switch or switch. Okay. Boom. Switch on or whatever. Okay, there we go. Is that good? This right here was, what was our resistance? 0.4. This right here is 1.2 ohms. This right here was 0.4 henries. No, 1 henry. Did anyone bother if I put an H? There you go. 0.4 F. Okay. VC. Okay. Is that good with everybody? Now, let's see. Let's see what we got here. Huh? Voltage. Let's do 12 volts. Right? And then right here, I'm going to create a pulse. So let's do our pulse. We're going to go from 0 to 1, turn on the switch. Let's give it a 1 second delay. Let's rise 1 nanosecond, fall 1 nanosecond, turn on for, 10 seconds. Okay? So we're going to turn it on. Now I got to create a dot model my switch SWR on is equal to 0.1. R off is equal to 100K. I don't know, I'm just guessing. VT is our threshold, is 0.5 volts. Okay, is that making sense? Pain? Lots of pain. VN, VX. Run. Let's run it for, 20 seconds. Can't find it. My switch. Run. Our switch turns on. Right? Look good, right? Turning on in 1 second. Let's see our VC. What is that? 8.47. That wasn't 9 volts. Did we calculate that correctly? Oh, you know what? This resistance is so finite. 1E minus 9. God, I'm so angry. There you go. Now I should run. Why is it taking forever? Simulation time, 5 seconds per... screw you. Anyways. Let me see. How do I make this run a little faster? I'm going to do the following, where our initial condition... Let's not do delay. I don't want to wait. No delay, okay? Initially, we're going to see this tank, or actually... I know you guys want to see that, so whatever. .IC, the voltage VC, right? Voltage at VC is equal to, what was it, 9 volts? The initial voltage in there, right? Is that good? And then our initial current, I'm going to do .IC, the current I in L1, okay, is equal to 0. Does that make sense? See, this helps it run. Simulation speed, slow. Is our current doing anything? Let's stop the simulation. I want to get things to work. 0, no delays. Let's move this guy. Run, run, run. Simulation speed. What's our current? Nanoamps. Look at our little guy wiggle. Oh, that's a ringing, all right. Okay, so you know what I think it's doing? So we got to go a lot more slower. Stop. Okay. Let's run for, I'm going to do 100 milliseconds. Okay. Switch on. Okay, that's good. That's good. All that is good. Do a transient. Let's do it. Call it 1 second. See what happens. What? Why is it so slow? Look at that. 1 millisecond. Arrgh. Oh, come on. Control Z. Why is it so slow? See that ringing right there? That's over damping. Is that making sense? What's going on? It's settling. If I were to look at this voltage right here, right? Going from 9, it's 9 volts. And why is my switch not turning on? 0 to 1. Oh, we need to close the switch. 1 to 0. There we go. Or open the switch. This should work. Does that look good? VC settles down to 0 volts, right? The current I is overdamped. Is that making sense? What I'm trying to show you guys is it's overdamped. Look at this. It's just wiggling up and down. Is that making sense? Did I punch in all my numbers right? Man, he's making you solve this problem. But yeah, based off this, omega naught. Let me see. Because omega naught says it's 5. A frequency of 5 hertz. That makes no sense. I'm using the right values, correct? 0.4, 1.2, 1 Henry, 4 farads. Initial voltage error is 9. I think I got everything right. Let me run this for 10 milliseconds, okay? And let me show you what's going on. Or 20. Let's show you settling and non-settling. I want it to... Okay, initially it turns on. Let's wait for 10 milliseconds. There we go. Let's see what happens here. 50% done. It's in the second half. I wonder what it's doing. Because I don't want to take this long. I don't like this. You see that right there? So you see how before the switch opens right now, it opens, correct? Or what is going on here? Initially it's closed, and then we open it. I don't like this. Let me show you what's going on. Okay. T delay, T on for 5 milliseconds, 5 milliseconds. Okay. Run it for 10. Run it. Let it run, let it run, let it run, let it run. I don't like this, y'all. Because you guys, if this is truly what's going on, omega naught is 5? That doesn't make any sense at all. Let me see. There we go. Okay. So let's explain. This right here is 9 volts, right? Our settling time, correct? Like, think of this as the switch is closed, okay? Now we open the switch and then it settles back to 0, right? We're seeing that overshooting, that overdamping. I think because this circuit is overdamping, LT Spice has to calculate all these little points. And you know it's going to be ringing, correct? Zoom the fit. Any questions? Yeah, I know. There's definitely an easier way to do this, but if this is what the circuit's doing, then so be it, all right? Any other questions? So next week, we're having another discussion, right? Should we have that as our final discussion, or should we do one during study week? Study week?
I'd like one if you don't mind.
All right. Yeah, because I'll be here. Well, that's why I'm always working here. So, yeah, we'll have one more next week and then one more on study week. And that's pretty much it, all right? Any other questions? All right, have a good day.